Okay, so let's take a look at this sample problem. So it says the long solenoid S has 220 turns per centimeter and carries current I is diameter D. As the center, we place a 130 turn closed D-pack coil C. Okay, so yeah, this one is the closed D-pack coil C, and this is the S. This is the S. This is the S here. Okay. The current in the solenoid is reduced to 0 at a steady rate in 25 milliseconds. So it means originally the current at S is 1.5 A and then reduced to 0 at a steady rate. 就是以一个均匀的速度去减到0，用了25个毫秒。What is the magnitude of the EMF that is induced in coil C while the current is in the solenoid is changing? Okay. Okay, so first we would like to calculate the magnetic flux. Okay, so phi B will be B times A. Okay, we just assume the B field is uniform. Okay, and for as long as it is a solenoid, it is mu 0 IN. Mu 0 IN. We have learned this in chapter 29 times A. Okay, so this is 4 pi times 10 to negative 7, and then times 1.5, and then times N. N is actually here 220 per centimeter. So 220 turns per centimeter means 220 times 100 turns per meter. Okay, so this is 220 and then with 2 additional zeros. Okay, and then times. Okay, so this for this cross-section area, we would like to consider is the cross-section area for C rather than S. Yeah, because we have a solenoid here, so and then this current will reduce, so there will be magnetic flux changing, so it will induce current for the coil C. So what we would like to find the EMF is here. So the cross-section area is of course regarding to a coil C. So here we have a pi. Pi, and then for coil C is 2.1 centimeter. 2.1 centimeter. So this is 0.021 over 2. Okay, this is diameter, so we divide by 2 is a radius, and then pi r squared by this. So this is nothing but 1.44 times 10 to negative 5 Weber. Okay, so this is the magnetic flux over this coil at the very beginning. And then the current will gradually decrease. So in such a way, the phi B dt will be negative 1.44 times 10 to negative 5, and then over 25 milliseconds. Okay, so the final phi B will be 0. At the very beginning is 1.44, so maybe I can write it as a 0 minus 1.44 times 10 to negative 5 over 25 milliseconds. 25 milliseconds or 10 to negative third power. So this is negative 5.76 times 10 to negative 4 Weber per second. Okay, so d phi b dt. Okay, so you can regard it as a division. Okay, so phi b is Weber, t will be s. Okay, so Weber per second. Okay, or you can also consider it's a fault. It's actually a fault. Okay, so finally, E equals negative n d phi b dt. So it will be, okay, we have two negative sign becomes a positive sign, and then the turns for the coil C will be 130. Okay, so 130 times d phi b dt, so 5.76 times 10 to negative 4 equals 75 millivolt. Okay. Okay, so we just simply demonstrate how to use the Faraday's law to do some simple calculation. Okay, so here we try to elaborate more about the Lenz's law. Okay, so here it says an induced current has a direction such that the magnetic field due to this induced current opposite the change in the magnetic flux that's induced the current. Okay. Okay, so here Lenz's law at work as the magnet. Okay, the magnet bar is moved toward the loop. The current is induced in the loop. The current produces own B field, and the magnetic dipole moment oriented so that to opposite the motion of the. Okay, so yeah, so this is quite lengthy. So here is let's try to show how to determine the direction of the current of the induced current. Okay, so we start from the top left one. We start from the top left. Okay, so here, increasing the external B field. Okay, so here for all this small figure, B, the B means the external B field. Okay, generated by something else, but we don't need to care about how it is generated. We only need to know that the B, this B is the external B field generated somewhere, and it can increase, decrease later on. Okay, but this is what we have at the beginning. And if we don't change the B field, okay, we won't have this B induced. As much as this B field is changing, then we will get this one, okay, according to the Faraday's law. So here it says increasing the external B field induce a current with a field B ind, okay, B induced that opposes the change, okay. So the direction of B ind is related to the direction of change rather than the direction of the B field, rather than the direction of the external B field. So if B field is increasing, then this B induced will be pointing upward to try to counteract to this change 所以这个 B induced 的方向的话是跟 B 的改变有关，B 的改变有关。现在的话 B 是指向下面，然后它会增大的时候，所以它的磁通量的话是向下而且增大，所以它会产生一个 B induced 是往上的，就是它想往下增大，我就往上拉它，不一定会拉得住但是它会想这么做所以就是 B induced 的话，在这个情况是往上的。Okay, so here it says the induced current create this field trying to offset the change trying to offset the change 就是它想往那个方向增加，我就拉它一下。Okay, so the next one is the finger are in the current the current are in the current direction and the thumb is in the induced direction. Okay, so you don't necessarily need to care about that. You know, okay, so actually, if we already know B induced is pointing upward, then the induced current should be like this. Okay, according to the right hand rule. Okay, we always do the right hand rule. Okay, so you just thumb follow the direction of the B induced, and then your thumb is your four fingers are following this direction. Okay, so for the second case, here the B field is the external B field is still pointing downward. But here we try to decrease the external B field. That will induce a B induced that opposite the change. So for all these four cases, it also mentioned that opposite the change. Okay, so it still keep opposite the change, but the direction are different. Okay, so here, if we try to decrease this B field, okay, which means the magnetic flux is still pointing downward but decreasing. So this B induced will try to also pointing downward to offset this change. 就是本来 B field 指向下面的，所以那个磁通量也是指下面的一个磁通量，但是它在减少，所以它是尝试去防止它减少。虽然它没办法完全做到，但是这个 B induced 的话，就是尝试就是我往下产生一个 B induced， 因为你往上了，就是你再往下再减少了所以我就往下去弥补一下，不一定弥补得到所以这个 B induced 就是往下。Okay, so in that case, we still use the right hand rule, your thumb pointing downward. So the induced current is like clockwise, it's still clockwise, like this. Okay, so for the third case, here now, if this B field further decrease up to here, and then try to increase to the to like pointing upward. Okay, so here the B field, the external B field is pointing upward, and it is increasing. So here the magnetic flux is pointing upward and increasing. So the B induced is still pointing downward. Still pointing downward like this case. Okay. So yeah. So for the first case, the B field is go to the maximum point and then it start to decrease. Okay. So here the B field start to decrease. Okay, so the magnetic flux is also pointing upward and start to decrease. So the B induced try to offset this change, opposes the change. So the B induced is pointing upward. Okay, so in that case, you use your thumb follow the direction of B induced. The current, using the right hand rule, the current is like counterclockwise. Okay, so this is how the Lenz's law operate. How to use the Lenz's law to determine the induced current direction. Okay, so here we have another sample problem. So here it says a conducting loop consisting a half circle of radius r equals 0.2 meter and 3 straight section. Okay. 所以就这里有一个半圆形有3端是直的 Okay, so the half circle lie in a uniform B field that is directed out of the page. Okay, so here above the dotted line, okay, we have some green dot, means the B field here is uniform and pointing out of the page. Okay, so but actually this is time varying. Okay, so the field magnitude is given by this equation, B equals 4t squared plus 2t plus 3. Okay, so this is not a constant, although this is uniform. Okay, uniform 的话是空间上相等，但是时间上的话它会时变的，就是叫做 time varying， time varying， 中文叫做时变。 10变. Okay, with B in Tesla and T in seconds, an ideal battery with EMF E bat equals 2V is conducting to the loop. The resistance of the loop is 2 ohm. Okay, so here we have this one. Okay, so 2 volt from here to here, and then there is a 2 ohm resistor over the whole loop. Okay, over the whole loop is 2 ohm. Okay, so it asks you what are the magnitude and direction of the induced EMF, and also at t equals 10 seconds. Okay, as this one is time varying. Okay, so the induced EMF or induced current is also time varying. So it just asks you the induced EMF at t equals 10 seconds. Okay, so here we try to consider E induced, but the absolute value, because there will be a negative sign, but the sign here is not very important. We can determine the direction of the EMF or the induced current using the Lenz's law or using the right hand rule, something like that. Okay, so here is actually d phi b dt. So this is a d dt phi b. As much as it is uniform, it becomes b times a, and a is a constant, so we can put it as a times db dt. Okay, so a is pi r square over 2. Okay, it is only a semicircle, so pi r square over 2, and then d dt. Okay, and then b is 4t square plus 2t plus 3. Okay, so take the derivative. Will be like 80 square becomes 40 square becomes 80, and then 2t becomes 2, and then 3 becomes 0. Okay, so like this, or pi r square 4t plus 1. Okay, just distribute these two inside. Okay, so the EIND at t equals 10 seconds. 10 seconds is like a pi r square, and then 4 times 10 plus 1. Okay, and actually r is 0.2 square. So this is nothing but 5.2 volt. Okay, for the induced EMF. Okay, so actually we also need to determine the direction. Okay, so we need to consider the magnetic flux. Okay, so for the magnetic flux of this part, B field is pointing out of the page, and whether it is increasing or decreasing, so we can simply check it here. All the coefficients are positive. Okay, so if t is increasing, when t is positive, we can expect that b is also increasing, and so as phi b is also increasing at t equals 10 seconds. So in that case, B field is pointing out of the page and also increasing. So B induced should be into the page. B induced should be into the page. B induced should be into the page, and the direction should be like follow the right hand rule. You use your thumb pointing into the page, your finger will be like clockwise. Okay, so this is like clockwise. So the current will be like this. Okay, so here it asks you what is the current in the loop at t equals 10 seconds. Okay, so what we also know is that this is 2 ohm, and then this is the IMF 5.2 volt, and then there will be I induced clockwise. Okay, but here we also have another battery. We need to determine whether this 5.2 volt is added with this or subtract by it. Okay. Yeah, this is not. Yeah, this is yeah a little bit confusing because yeah for this is an EMF. This is also an EMF, but yeah the I induced due to the induced EMF is hot rise. But if you just ignore the EMF first, you just consider this one. Okay, if you have only this, if you only have this loop with this battery, okay, the current generated by this battery will be like the current is counterclockwise. Okay, so we get the knowledge about that is I should be like E net, the net EMF over the whole loop should be as subtraction E induced minus the E battery over the R. Okay, so it will be 5.2 minus 2 over 2. Okay, so it is 3.2 over 2 is 1.68. Okay, so considering the direction of the EMF or direction of the current or yeah, something like that, should be more careful. Especially if there is an other independent battery there. Okay, so here we have another sample problem. So here it says the figure shows a rectangular loop. 就是有一个长方形的圈 of wire immersed in a uniform non-uniform and varying magnetic field that is perpendicular to and direct into the page. 就是在一个又不均匀又时变的time and varying magnetic field. The field magnitude is given by this expression. Okay, so B is related to the time and also the x-axis. Not the y-axis, hopefully. With B intensity T in second and x in meter, the loop has width W to be 3 meter. Okay, this is 3 meter, and then H is 2 meter. Okay, what are the magnitude and direction of the induced EMF around the loop at T equals 0.1 second? 0.1 second. Okay, so first we would like to find a phi B equals integration of B dot dA. Okay, so this time this is not a constant or not uniform, so we need to use the integration rather than a simple product. Okay, so but at least B and dA will be perpendicular. dA is also, we can consider dA is pointing into the page, so this is the positive direction. Okay, so in that case it is B times dA. Okay, so here dA it is a Cartesian coordinate， 就是这个直角坐标系。本来 dA 的话就会变成 dx dy， 但是这个跟 y 无关的话，我们就可以只切这个直的长方形。So we only need to cut it along the y-axis because the B field is nothing to do with the y coordinate. So which means dA originally should be dx dy, but here we can make it like the h. Okay, so this rectangular have a uniform B field there, because it's only related to x. We cannot include too much across the x-axis, but for the y-axis it's all the way uniform. So within this orange rectangle, okay, the B field is uniform. So here we should have something like h times dx. Okay, so the height is h the width is dx. Okay, so dA equals h times dx. So which is b integration of bh dx. So the dx will integrate it from 0 to 3 meter. 0 to 3 meter. Okay, so we can plug in b to be 4t square x square, and then h dx from 0 to 3. Okay, so h is actually 2 meter. So we have h equals 2. So altogether h2 times 4 will be 8. And then t is independent to x. Okay, so t squared we can put it out. Okay, so the remaining stuff is x squared dx from 0 to 3. Okay. So x squared integrated becomes x cubed over 3. So at squared, and then 3 cubed over 3. Minus 0 cubed over 3 is 0. Okay, so this is nothing but 72 t squared. Okay. Okay, so the absolute value of E will be d phi b dt. d phi b dt. It is a single loop, so n equals 1. So d dt, and then 72 t squared, which is 144 t. Okay, so here E at t equals 0.1 second will be 144 times 0.1, which is 14.4 volt. Okay, so this is the magnitude, and what is the direction? What is the direction? Okay, so here we can also see that the B field is into the page. For T is a positive value, and also X positive. Actually, B, yeah. So for T is a positive value. Yeah. So the B field is actually increasing when T is increasing. So we will expect B field or B magnetic flux is pointing into the page and increasing. So B induced will be like pointing out of the page. B induced is pointing out of the page. So in such a way, you use of pointing out of the page. Your four fingers are like counterclockwise. C-O-U-N-T. Counterclockwise. Oh, counterclockwise. Okay, so like this, I induce will be like counterclockwise. Okay, any questions? Okay, so here we talk about the induction and energy transfer. Induction and energy transfer. So here it says we have a rectangular loop of wire of width of width L. Okay, actually, yeah, L. You can consider this a height. Okay, so has one end in uniform external B field that is direct perpendicular into the plane of the loop. This field may be produced by a larger electromagnet. OK， 所以他是说，就是有一个位置的来源产生一个 B field 指向那个 into the page 的。Okay, so the dashed line is the figure shows the assumed limits of the B field. The fringing of the field edges is neglected. 只有在里面有，外面就忽略。You are to pull this loop to the right at a constant velocity. 那本来的话就是这个圈有一部分在这个 B field 里面，然后你就那一根线在里面，一根线在外面，那你就尝试把它拉出来会怎么样？Okay, so the okay, so according to chapter 28, okay, the second version of the Lorentz force, we know that if you see remember we have FB equals RAL cross B. Okay, so this is the second version of the Lorentz force. Okay, so here we can try to see whether there are any force acting on the wire. So here we don't have any B field, so no force acting on this wire. And for this one, okay, we have a so first we need to determine the current. Okay, so actually we assume the B field is pointing into the page and doesn't change. Okay, this uniform B field is a constant B field. We try to prove it out so that the loop overlap with this B field will be decreasing. So which means the magnetic flux is also decreasing. Okay, so if the magnetic flux is decreasing, so the B induced should be like into the page, so that to offset this change. Okay, so this is the B induced. So if B induced is into the page, you use a thumb pointing into the page, your forefinger is like clockwise. So we know that this induced current is clockwise. Okay, so if I is clockwise, okay, for the upper segment, okay, we have L pointing to the right side, and then the B field pointing into the page. So L cross B is pointing upward. Okay, so we have F2 pointing upward, acting on these parts. Similarly, for this one, L is pointing to the left side, okay, because the current loop is like this, going to the right side, going down, going to the left. Okay, so L for this part is pointing to the left side. So you use a thumb pointing to the left, you use your forefinger pointing to the left side, and then you cross it into the page, your thumb is pointing downward. So F3 acting on this part will be pointing downward. And actually for the L for this part and this part will be the same, the B field are the same, and then also the current are the same. So this F2 and F3 have the same magnitude but opposite in size, so these two forces cancel each other. And finally we have this one. L is pointing upward, so L cross B, L pointing forefinger pointing upward, pointing into the page, of thumb is pointing to the left side. So F1 acting on this part is pointing to the left side, which means you try to drag it to the right side, but there will be a force holding it to make it a constant velocity. So we assume this is a constant velocity moving to the right side. So you used to provide a force equal to F1 so that to make this movement to be constant velocity. Okay, so there will be a flux change as what I've mentioned, and then there will be weight of work, so which means that you need to have a force equal to F1. This F1 is nothing but I times L cross B. Okay, so you need to provide a force with this velocity. So this is the rate of work， 就是这个是叫做功率，它不是功的话是 W equals integration of F dot ds。那如果是功率 P 的话是 integration of f dot dv dv， 所以这个就是对于这个怎么说，就是 P 等于 dw dt. Take the derivative of the work done with respect to time. Okay, so it is like a d dt and then integration of f dot ds. So you put this one to here, so it becomes integration of f dot ds dt. Okay, so this one becomes velocity. 所以这个功率的话，就是单位时间做的功。Okay, so here we consider the consider induced EMF. So first we have phi b. Phi b will be b times a. Okay, we just assume the B field is uniform. Okay, so and then the A will be like L is the height, and then X is the part inside the B field. Okay, so this area, okay, we consider this area to be L times X, and actually the V is moving to the right side, so which means that dx dt is like negative v, something like that, or v. Actually have v. Okay, so we have a equals L times x is the area of this part. So plugging this one into the Faraday's law, d phi b dt, d dt, and then blx. Bl will be a constant, so we have a dx dt. Dx dt will be the velocity. So EMF, the EMF for this work, or actually due to this action, will be B times L times V. Okay, so here we also assume that the collective resistance 就是整个圈的电阻 okay, the overall resistance for the loop will be R, so I, the induced current, will be the EMF divided by the resistance, so BLV over R, nothing special. Okay, so here we make use of the this one. Okay, F equals F1 equals IL cross B, I times L cross B, which is the Lorentz force. Okay, so and then sine of 90 degrees, so sine of 90 degrees 1. So F is ILB. So from the previous page, we already have I. I is having this expression. So we plug I here, so BLV over R times LB. So finally we have B squared L squared times V over R. Okay, and finally, power will be F times V. So finally B squared L squared V squared over R. Okay, will be the rate of work or the power So here the note is that the work you do in pulling the loop through the B field appear as thermal energy. 就是如果你真的在做这个实验的话，你要做功嘛，你要做功把它拉出来，但是它会有一个电磁力把它拉住。所以你要用力把它匀速拉出来，然后这个中间会消耗一些功率， 那这是功率的话就会变成热，就会被这个圈的内电阻所消耗掉，内电阻所消耗掉。那这个是速度了，这个是速度，它也会等于 I 平方 R 啊，或者是V 平方除以 R 之类的。但是那个 V 平方跟这个 V 平方是不同的，这个是速度了，那个是电压。Okay, so this is not difficult. And then here we also talk about something called the eddy current. Okay, eddy current in Chinese is called 涡电流，就是漩涡的涡电流。Okay, so here it says as you pull a solid conductor， 就是一个整片的 conducting plate， 这个导体的盘子out of a B field， out of a B field, not file. This one should be field. Eddy currents are induced in the plate. A typical loop of eddy current is shown. OK， 所以前面这个例子是说，我们从一个 B field 里面拉一个线圈出来，它有电流。现在的话，我们如果整片导体把它从一个 B field 里面抽出来的话，它会产生一些所谓的 eddy current， 它会产生一些 eddy current， 就在里面自己在旋转，就是好像在一个水里面，它有一个漩涡一样那种感觉。它就是透过这个法拉第定律所产生的，因为在这里的话，它就会有所谓的d∅bt 所以它这里是要表达一个意思是，你不需要有一个导线的通路，只要它有一个空间给它去走的话，它自己就会产生一个涡状的电流，就是它就是绕着一个地方去转，绕着一个地方去转。Okay. Okay, so here we also try to introduce something called induced E field, or we try to write the Faraday's law in a generalized form. Okay, so using the induced E field, we can write Faraday's law in its most general form as this one. Okay, so somehow similar to the Ampere's law. Okay, on the left side it is a line integral. Okay, so recalling for the Ampere's law, it will be like integration of B dot ds will be mu 0 I enclosed. Okay, so on the left side, okay, for the Ampere's law is a line integral of the B field. Here is the line integral of the induced E field. Line integral of the induced E field. 那其实两个都是产生嘛，就是这个的话就告诉你说哪里产生这个 B field， 就是透过这个 I enclosed 来产生的。那这个会有induce 一个 E field 的话，是透过这个实变的磁通量来产生的。OK， 所以这两个左手边是类似的它一个是产生 B field， 一个是产生 E field， 但是这个的话还没结束的，这个是32章的时候还会讲后面一半的，So here is a highlight. It says a changing B field produce an electric field. Changing B field produce an electric field. And then also in chapter 32, you will also learn changing B field changing E field will generate B field. Okay, so it is yeah, something like this. Okay, so this one, the first one is the Gauss law. Okay, the first one is the Gauss law. Although all of these are differential form, not the integral form. Okay, so the second one is also Gauss law, and then this one is the Faraday's law. Okay, the gradient cross this E field is the negative partial B partial T. Okay, so this is like this one. Although it's a partial derivative, this is a partial derivative here. Okay, so for the Ampere's law here, okay, gradient cross B field is mu 0 J. Okay, so you only learn up to this part only. You only learn up to this part only. So mu 0 J. But in chapter 32, you will also learn this part. This part is the displacement current. This part is the displacement. This one is the static current. So this is the current density referring to the static current. Okay. So for this part, it tells you that if you have a time varying E field, okay, it will generate E field. Okay, so something like that. So today I intentionally picked this close. Okay, so here it mentioned that this is very important. So for the electric potential, you learn in chapter 24. You learn in chapter 24. So if you still remember, we have an equation like this: V equals negative integral of E dot ds. So this is the electric potential, and at that time, we tells you that if you go for a closed loop, okay, it will be like integration of E dot ds will be zero, will always be zero if you go through a whole loop. So at that time, it means that we don't consider any B field. We don't have any B field or time varying B field. So that the potential difference only related to the starting point and the end point. So which means for the electric potential we introduced in chapter 24, okay, so induced electric field are produced not by static charge, but are changing magnetic E field. Therefore, potential difference has meaning only for electric field that are produced by static charges. It has no meaning for electric field that are produced by induction. 所以要注意的是，如果你考虑的这个环境里面只有静电荷的话，那你去想这个才会对。如果你现在有一个十变的磁场，十变的 B field 去产生电场的话，那你再去考虑这个的话，肯定会想错，肯定会错的。因为在24章的这个环境底下，我们是有这一个的结论的，就是 E 到 ds 的话只跟起点终点有关，如果起点跟终点是同一个点的话，它一定是零的。但是这里的话就是这一个 E 到 ds 它就是要跑一整圈嘛，但是跑完一整圈之后，它是等于这个 negative d phi b dt， 所以有一个十变磁场、十变磁通量的话，它就会有一个非零的值所以在这里有十变磁场的话就要注意不要再去想这个东西。你想这个东西可能你想的很觉得很完美，但是肯定会不对。OK。